My name is Eli. This is Matteo, and we did most of the work when we were in Brown. I'm still in Brown. Matteo now moved to work for Sigma. And we're going to talk about this general idea that doesn't actually appear in the title, called uniform convergence, which Rademacher averages and this dimension are an example of that. And I will say a few words of introduction to this. So as you probably noticed in your career, some of you have a longer career, shorter career, we often have a phenomenon in computer science when something starts as highly theoretical, obscure mathematical concepts. And then slowly it moves to be a research area, and eventually it becomes a practical area. Think about dimensionality reduction. So when the first papers in mathematics were published, I'm sure no one in computer science ever noticed. The Johnson paper, and no one thought it has anything relevant to anything we're doing. Later there were obscure theory papers published in theory conference like so-called folks, and eventually it became an everyday tool that most companies are using. And here we are in the same situation. We are about halfway of that situation. So these two concepts started as highly theoretical. VC dimension was later, but was really introduced in order to distinguish between infinite and finite something, which doesn't sound like very relevant to computer science. Same about the Rademacher complexity. We are now in a position where it is a research area in data mining, in machine learning, in computer science per se. And there's a very good chance that sooner or later, or you already see some of it, really moving into real applications. And so, in a sense, you are in the exact place and time to, get aware and understand what it is, because, we're soon going to see it more and more in, real applications, in particular data mining. And this presentation, so you probably know that VC dimension was introduced to computer science through learning, but our interest here as part of KDD is more in data analysis. Okay, so we'll talk a little bit about VC dimension and learning, but the real focus of what we're doing here is using these tools into data analysis. Okay. So what we're going to do here in this, 3 hours or a bit less than 3 hours that we have. So I'm going to start from a very, very high level. So obviously, people here come from various different backgrounds. Some of you might know all the introduction and want to see right away, all the details. But I assume some of you are not. So I'm going to start with a very high-level introduction, and I'm really, at the beginning, will try to convince you that this whole issue of statistical learning is very relevant to what you guys are doing in data analysis. And you really should think and understand what is there and how it's related. And then, of course, all these tools are related to the general concept of sampling. So we'll talk a little bit about why do we sample at all. If we sample, what are the results of what we get out of sampling, and then how it's related to the issue of uniform convergence. And then we'll move into more of a technical discussion, and you'll notice as the slides are converting from PowerPoint to LaTeX as we move to the more technical part. And then I'll introduce, the formal definition of VC dimension and Rademacher average, why it's related to what we're doing, how do we use it, and some of the main theorems. Most of the stuff will be without proof, although here and there, I'll try to give you kind of the high level of, why you would expect it to be correct. And then in the second part of the talk, or this tutorial, Matteo is going to present some very concrete application of this technique to data mining or data analysis techniques. In particular, to two problems, the frequent item set in the various, so you all probably know the frequent item set is like a kind of a benchmark in data mining. So various questions related to frequent item set. Matteo will show how you can get a much more efficient and more robust algorithm using some of these tools. And then to question of betweenness, centrality, and other analysis on graphs. So the first one is analysis on items, and here you'll see also an example of analysis on graphs, which use this kind of techniques. Okay, that's kind of the high level of what we're going to do. We're going to start from relatively simple, high level, kind of a PowerPoint presentation, and eventually, we're going to move to the real mathematics and to the real details. Before we start, since we're going to talk about sampling, there's one thing that we all know in the background, but it has to be stated very carefully here. So there's actually two approaches to data mining or data analysis. We kind of know this, but we kind of ignore it from time to time. So data mining as an area started from database people. And database people look at, here's the data, this is the data, this is what I have in my database. That's the data. There's nothing else other than what's written in my database and what question I can answer on that, okay? In contrast, most data analysis, at least, in particular what we call the scientific approach, is ingrained or is built on the idea that whatever I have is a sample of some, larger phenomena. Scientists take measurements, and the question that the scientists would like to answer is not what I saw in my measurement, but what are these measurements tell me about the underlying phenomena, okay? And both approaches are valid and both approaches are good. There are places here. You can take 6 from here, move it back if you're afraid to sit in cold. From here, yeah. So, it's not that one approach is the correct one and one is not. There are different approaches fit into different applications. So this database approach is the right one when you do something like anomaly detection, okay? So if you look for a crime, okay, so here is the NASDAQ transaction today. Is there an anomaly there, okay? There's nothing I'm going to learn from that about the future, or sometimes I have to learn from future crimes. But the particular thing is, here is a sequence of transactions, and maybe there's one transaction there that is a crime, okay? And it stands out this way or another, okay? Now, there's no way you can solve this problem by sampling. There's no way you can solve this problem by generalization. Okay, there is one thing that you're looking, there's one needle in the haystack, okay? So, and that's where what you have is your data. There's nothing you're going to generalize from that. There's nothing you're going to learn about the future. There's something you have to do in that data. Okay. But that's important. A lot of security problems fall there, a lot of protection, but that's not the core of data analysis. The core of data analysis is I look at the data, and at least in the machine learning, the phrase is generalization. So I'm looking at my data, and I think about it as a training set. And the question is, what can I generalize from that? Okay? So the data is inherently a sample. Okay? Even if I don't think about it this way, it's a sample. Okay? It just might be a bigger or a smaller sample. Okay? So here, our data, whatever we have, is a sample of a larger phenomena, and we want to learn from the sample. So why do I emphasize it? Because the next slide will ask, well, why do we sample? What do we get out of it? Well, in most applications, anywhere we're sampling, our measurement are sample. Now, even if you look at your database, even if you look at the database approach, there's still a lot of questions there that you can answer by sampling. If you're looking for one unique event out of a billion transactions, there's nothing can help you with sampling. But if you want to answer questions like, what's the average salary, what's the 10%, higher salary stuff, you can still sample and gain a lot. Okay, so these are these two ways of looking at data. And now this question of sampling. So sampling kind of came late to computer science, although in other areas, this was done all the time. Okay, so so there's this distinction. This was a caricature that I couldn't find when I was building it, but when I was doing the presentation, where you have the database, or think about it as the computer industry executive and the statistician. And here come the manager and say, wow, our data is double this year. And database guy said, oh great, we have to buy more machines. And the statistician says, well, nothing changed, we just get better results. Okay, so that's two ways to look at it. Okay, so so sampling is the idea that, and it's a very powerful idea, is the idea that no matter how much data you have, there's really no reason to look at all the data. There is some, golden ratio, some kind of, minimum that I need in order to get a good valid results. Okay, if I just sample correctly. Okay, so analyzing sample instead of the whole data set can save huge computational time and also a lot of space. Most of you probably know the item set problem that we'll discuss later. So anything about finding frequent item set, correlation rules, stuff like that, require a huge amount of memory. Okay, so if I can do it on a sample, I can save a lot both in computation and space. Okay, but obviously, if I'm sampling, I'm approximating the solution. Okay, so so when I'm analyzing a sample, I get an approximation of the two results. Okay, and the statistician, the non-Bayesian statistician, look at it as there is some true value that only God knows, we'll never know it, and we'll just get closer and closer to this as we get more and more samples. Okay, but the truth is actually no one ever going to know. Okay? Okay. And so we sample. But now comes the main question, and this question is really, to a large extent, unique to computer scientists because from some weird historical reason, statisticians think about it differently. So our question is, how good is the approximation that we obtain by using a sample? Okay, so when you look at the newspaper and there's the public opinion surveys, at least in the States now, it's very important. The election coming, all these crazy candidates, so we always sample. They always, try to predict, and most of us don't look at the small letters at the end of the article. But if you're in a serious newspaper like the New York Times, at the end it will say, well, this was done using how many sample? What sample size?
1,500.
Well, it's always around 1,000 something. And actually, you can see, when I teach it in the course, I'll show you how to get this 1,000. It's always 1,000 something. By the way, independent of the size of the population, which you probably know that. And then, there's, with the way they write the newspaper, only 1 out of 20 times, the result will be off by more than 5%, or in a mathematical way, so there's only 5% error, 5% probability of an error more than 5%. So this is the kind of thing we want to get. Okay? So if I take a sample of a particular size, I want to know, how good is my sample? How good is the gross probability to be far by more than some percentage? Okay. Can I answer this question? Or how to answer this question? This is actually the core of what we're going to do here. It's trying to answer this question. How to relate the sample to the result. Okay. Okay. Intuitively, we kind of know that if we increase the sample size, we get better results. Okay, by the way, historically, this was not so obvious. It's only this century that we all kind of born with this idea that the more experiments you do, you get better results. This was not known to the medieval people, even to scientists. Okay, this is kind of, now it takes for granted, but, okay, so we know that if you get more samples, somehow we'll get better results, okay? The real question that we have in computer science is, can we actually quantify this relation? Because sampling is a cost, okay? Sampling is a resource, it's like memory, time, and so I want to relate my resource, how much I invest in the work, in order, I want to relate it to the quality of my results. Okay, so more formally, we want a statement when we analyze a random sample of size n with probability 1 minus delta, the results are within an epsilon factor of the optimal, and for those who know what I'm talking about, we'll sometimes have additive epsilon, and sometimes it will be multiplicative epsilon. We want both type of results. Okay, and I apologize for epsilon in PowerPoint. It's awful. We move later to LaTeX where epsilon looks like epsilon. Okay. So we want to answer this question. And when we try to answer this question, we see that there's a problem. Okay? Just having the now sample size is not enough. There is another ingredient that is needed. There's another thing that is needed in order to answer this question. Not surprising, it's related to what is it that we want to analyze. Okay, so there is this trade-off which is fundamental to all the work that we have here. So we have a sample size, we have the accuracy that we want from the result, but then come the third component, which is some measure of the complexity of what we're trying to analyze. Okay? So VC dimension, Rademacher averages, and the other tools are, in a way, a measure of the complexity of what you want to analyze. Okay? How complex is what you're trying to do? These are measure of complexity. Therefore, by the way, in computer science, Rademacher averages became Rademacher complexity. But actually, the real name is Rademacher averages. Okay? So these are two measures of complexity of the analysis task. Furthermore, if we know the VC dimension or the Rademacher averages for a particular problem, then we actually can get tight results. So if I know that the VC dimension is D, and I have a sample n, then I can tell you the epsilon delta of the approximation within, some approximation. There's some log thrown there, but it's almost tight. And the same thing about the Rademacher averages. So in a way, what we have here is we have tools that tell you, if you understand this measure about your computation problem, the analysis problem, then if you tell me what sample that you have, you can actually write a theorem and say, my result is within epsilon with probability 1 minus delta and so forth. The type of result we want to see in computer science. Okay. Okay. We'll distinguish here between two types of analysis. The first one we'll call detection, the other one we call estimation. Okay? And they are related to the two major tools that we do with this technique. So what's detection? So, you have internet flow, so that's actually a real problem. So you have a gate, a routing gate, you know, Hilton give you free or not free internet, internet access, but tells you that please don't use more than, I don't know, gigabyte per second. Now they have these hundreds and hundreds of users, and they want to detect the criminals. They want to detect the people that are using too fast. Okay, so that's a detection. You know, in an AI solution, you'll have to keep a count for every user. That's going to be almost impossible because all this has to be inside the routing device, so it will slow down the device. So you need some, you know, smarter way to detect, you know, the high loader on the system. That's an example of detection. We'll see in a while that learning, particular learning and classification, is also equivalent to detection. In a way, it's detecting those cases that, those rules that are not the correct one. Okay, we'll see. The detection fall into this, learning fall into this detection. Then the other one, which is more related to data mining and more challenging, is estimation. Okay, so you have, you know, internet. You have browsers. Okay. Unfortunately, the problem these days is not that sophisticated because there are about 2 or 3 browsers that control the market, but assume that there were many browsers. And you are some kind of a consulting firm, and you want to know, you know, what are the ratio of the market that belongs to each of the browsers. Obviously, you cannot look at all the communication in the world. You'll have to sample it somehow. And you want to know, you know, how good is your sample, okay? And here's something that you'll hear again and again. You are not asked to sample and decide how many people use Microsoft browser. You are sampling and have to answer for all the browsers simultaneously, what are the ratio of people who are using them. And this will be the repeated thing that we'll have through this tutorial. That's where the complication is, okay? And equivalent, another question that will come later in the application is find the top frequent item set. And again, something that I'll say again and again later, in order to find the top 5 frequent item sets, I don't only estimate the top 5 frequent item sets. In a way, I estimate all possible frequent item sets in order to find the top 5. As we see, this is the core of all the complications. Okay, so, and here's a little bit more formally. So, I know how to detect a particular event, okay? So let's R be a set or event, okay? I know that if I, you know, if I do 1 over epsilon, ln over epsilon, 1 over epsilon, never mind the detail, you know, random trials, then with probability, the probability that I don't hit R at least once is bounded by delta, okay? So that's 1. For a particular event, okay, I know exactly how many trials I need until with probability 1 minus delta, I'll hit it once. The same about estimates. This is basically a version of Chernoff-Brown. You know, if I want to estimate the size of a set, then you know about this number of it should be gamma squared. This number of iteration will give me you know, that with probability 1, at least 1 minus delta, I hit that element. Okay, so we know that. We all know that. And we can also write it in a little bit more mathematical way, which would be very useful in many of the applications. So instead of talking about it as sets and uniform distribution, you can think about having a ground set U and having a distribution D on U. And all the sampling now are not uniform, but are sampling according to distribution D. Okay, and then the results are basically the same, because now epsilon is the probability of the event, okay, and everything else goes through. Okay. So this is what you all know. We all learn it in some basic probability course. Okay. Why this doesn't solve a problem? Okay. Okay. So the reason it doesn't solve a problem is because all these tools are good in order to estimate one particular event. Okay? But what we need is we need a sample that estimate many events simultaneously. I want to have one sample that would answer not only the frequency of F1, but the frequency of F1 and F2, F3, and F4. All of them will be correct within epsilon with probability 1 minus delta simultaneously for all of them together. Okay. Okay, so we need a detector or an estimate that works uniformly on a lot of events, simultaneously. So that's the problem, and that's very much inherent in our data mining or data analysis. Almost all the interesting problems that we work with fall into this category, that there are large number of events that we have to estimate them together. Okay. So this brings us to this notion of uniform convergence sampling. So basic sampling results guarantee that a sample intersect or approximate one given event, when it's not too small, of course, so it has to be, say, greater than epsilon, okay? But in data analysis task, we need to sample we need a sample that intersect or approximates simultaneously all events, okay? And so we have two difficulties here. One is, well, we need to estimate more than one event, and the events are not fixed in advance. Now, for those of you who are very fluent in probability, that's a major issue. So you want, if you have the event fixed before you take the sample, then you can do the computation. But if you don't know what you are estimating before you take the sample, you have to estimate many events, or the possible incarnation of this event. Okay, we'll see example in a second if it's fuzzy at this point. But that's another major issue. Okay. Now some of you might sit there and say, well, but we know how to do it. We take union bound. Okay, if I have a good bound for one, and I have to estimate 100 events, well, I take a union bound and I have to take 100 times the sample. Okay? Well, that's good as long as the number of events is relatively small. We'll see in a second a case where the number of events is actually infinite, but you'll actually do it very efficiently if you just do it correctly. Okay, so union bound, even on, you either have a lot of events. For example, think about all the possible item sets, including those that never actually appear in the data. So, the supermarket has 10,000 products. Every subset of these is a possible item set. So now you have to union bound on all of them. Well, that's too hard. Okay? And we'll see in a second that sometimes you actually work in a case where straightforward definition of the events actually gives you infinite set of events. And then you'll see that even though it's infinite, you can actually detect very, very efficiently because of this structure between the events. Okay. Okay, so let's start with, so there are two examples that I'll do in the theory part, and then Matteo will have, well, one of them almost Matteo used, but the other one is not here. Okay, so the first one is when we look at detection, then the obvious example is to look at classification. And I'm going to simplify this. This is not a tutorial on machine learning. I want to simplify it to just focus on the role of the sampling. Okay, so here is, in 5 words, the whole idea of pack learning. So you have a probability distribution on a domain U, okay? And you have a partition C of U into the red and blue, or the in and out. The in and out is because we'll have a classification as a bubble. So those are in will be the blue one, those are out will be the red ones. Okay? So there is some classification that God knows, we don't. Okay? And then we're getting some class of possible classification, might be very large. Okay? All Boolean functions, all intervals on the line, or whatever, all possible classification. And we require that the real classification, little c, is given, is part of the capital C. In the machine learning, this is called a realizable case. It's not needed, but for our case here, makes life simpler, okay? And then, of course, we get a training set. So a training set has m example. Each example is an element and its classification, okay? And the important thing is that the elements that are used in the training set were sampled according to distribution D. So you cannot cheat me by giving me example of some irrelevant area of the domain. Their X are sampled from the domain according to the distribution. And the goal is, with probability 1 minus delta, I'll give you an algorithm that generates a classification that is correct with probability 1 minus epsilon. What does mean correct with probability? If you give me new examples from the distribution D with probability 1 minus epsilon, I'll give you the correct classification. So you taught me from a distribution, I can answer question from that distribution. Okay, if you take a baby to Alaska and he learns about animals in Alaska, he would come to Australia, he would never have seen a kangaroo, and he will not know that it's an animal, okay, or what it is, okay? So it has to be in the same distribution. And what's the 1 minus delta? 1 minus delta is that your sample with probability can be biased even if the sample is correct. Even if you sample according to D, there is some probability that all the samples were hit on a particular point. Okay, so that's the idea. Okay. So here, let's look at it as a picture, okay? So here is the real classification. Okay, so we classify the blue and the red. We want to distinguish between blue and red, okay? So there is one classification here is correct one, but what you get is you get many other classifications to make the drawing easier. There are only 4 different ones, but I can give you many more, okay? So again, you get all these possible classification. One of them is the correct one, okay? And I also get samples, okay? So before you didn't see any of this, you just saw the classification, the bubbles, okay? Now I give you samples of the yellow points, okay? Now what do you do with a sample? So you look at this sample, and it tells you, well, this point is red. Oh, if this point is red, then this bubble is definitely wrong because it's inside, and inside is supposed to be blue. Okay, so this sample eliminates this one. Okay, now if you get this yellow down there, it tells you nothing because it's red and it's outside all the possible classifications. So, well, we know it's red, it doesn't help us. Okay. And then we get this one, which is blue. It tells you, oh, this point is blue. Yeah, but this point is actually inside all the classification. So again, it's not very useful information, okay? Now, how do I guarantee that I get the correct one? For any incorrect classification, I need to get a sample that will show me that it's incorrect. How does a sample that shows me that the classification is incorrect? It has to be in the difference between that classification and the correct classification. Okay, so for every classification, I need to get a sample between in the difference between that classification and the correct one. We'll formulate in a second, so we'll see why. Okay? So when does a sample identify the correct rule? So we have the concept class, a collection of possible classification. C inside capital C is the correct rule. For any other hypothesis, let D be the difference between them. Okay? So a delta of CH is all the points in which H of X and C of X don't agree. Okay? Now obviously if I get a sample inside delta of CH, then this sample would show me that H is wrong. Okay? So we need a sample that intersects every delta for all the H, okay? But not really all of them, because remember my classification might have some error. It has to be correct with probability 1 minus epsilon. So I need this to be true for all the deltas that are greater than epsilon. Okay? So I don't know if you can see the last line, but we'll see it again later. This brings the definition of epsilon net, which is the crucial tool in this dimension. So, did I do it again? No. So, an epsilon net is a set S. For us, it's going to be a sample, but it also can be a deterministic set, such that every event that is not too small intersect with this set S. Okay? So I have a domain, okay? And out of the domain, I want a small set that intersect with every event that has probability at least epsilon. Okay? That's the epsilon. You'll see it again and again. Don't worry. Okay. So let's start with trivial result, which looks like it solves all the learning problem until you see that it's actually meaningless, but we have to put it there. Okay? So any concept class C can be learned in number of example, which is logarithmic in the size of the concept class. Okay? Why is it true? Well, we need a sample that intersect every set with probability greater than epsilon. Okay, so now if you do the calculation, we won't go through the mathematics. If you do the calculation, then these are the number of concepts. This is the probability that M samples miss a particular concept. So that's a union bound, and if you chose the size correctly, then with probability, the probability that there is any big set that we didn't intersect is bounded by epsilon. Okay? So this seems like, wow, we can learn everything in log of the size of the concept class. Is it interesting? How good is this bound? Well, I'll show you this bound is useless. Okay? So this is a very practical question. Okay? You want to know what temperatures your iPhone is working. Okay? So, well, we are scientists. The only way we can do it, we sample temperature. So we know the iPhone definitely doesn't work below minus 100 and above 100 Celsius. I don't know how to translate to Fahrenheit, but Okay, so you know that beyond 100 Celsius it will burn, and below minus 100 Celsius, well, you're not going to live there, so it's not important. So we have a bounded interval, and we sample points on the interval, and we cool or warm our iPhone to that temperature, and we see if it works. Okay? So now we have the values in which it didn't work, and then there are a few values in which the iPhone worked, and then the values that it didn't work. Okay? So what are we trying to learn? Before we get to the formalities, what are we trying to learn here? Well, we're trying to learn a sub-interval on the interval minus 100 to plus 100. Okay? How many sub-intervals there are? Well, if we assume that the subintervals have to be in integers, then there are, 200 square such intervals. If we assume the interval is in real, there are infinite number of intervals. Okay? In both cases, it's a lot. I'll show you that you can actually learn it extremely fast. Okay? And in particular, the learning algorithm would have nothing to do with how many intervals we actually have there. And this will be our introduction to the VC dimension, because that's an example where the VC dimension overrides our union bar. Okay, so here is the algorithm. Okay, so okay, we did this. Okay, let's go through. Okay, a universe U is the interval AB. The endpoints are inside some interval, subinterval AB. The outside. A concept class is any collection is any subinterval. And so now when the algorithm will be wrong, okay, if the algorithm return an interval xy, then, okay, so here is xy, okay, and here is a and b, which are the real interval, okay? So if our algorithm gave x, but actually the real value is a, what does it mean? It means that there was no sample in that interval. Okay? Okay, so the algorithm is wrong on the area, the difference between the outcome of the algorithm and the real one, area that did not have sample. So now we'll show that this has to be small. Okay? Okay. So now we'll show that there is a learning algorithm that give a sample, given a sample from D, in our case a uniform on the interval, that use just this number of samples. Okay, so this is a function only of epsilon and delta, nothing about the length of the interval. And with probability 1 minus epsilon, return a classification, an interval xy that is correct with probability 1 over delta, 1 minus delta. And again, I just want to emphasize this whole example is just to show that the sample size is independent of the size of the concept class. We have nothing here that related to how many intervals we are trying to exclude. Okay. Okay, I'm trying not to do too much of the proofs here, so I'll just give you a high-level idea. If you don't get it, this is in all books and stuff. So. One possibility, there are many ways to answer the same question here, but once we take the xy that includes all the endpoints. So take the minimum xy that include all the points in which the iPhone worked. Okay? So obviously the algorithm can only err in the fact in that there are other points in which the algorithm worked, but they were not in the sample. Okay, so it only errs in one direction. Okay, so now let me look at the. So let's look at the picture. So we chose xy. Okay, the real thing is actually the real thing is AB. Okay, the correct one we chose xy. So now let's do, just for the sake of the proof, let's define an interval below A and above B. Each interval has probability exactly epsilon over 2. Okay? So I'm fixing this interval. Okay? Now, if xy is wrong by more than an epsilon, then it has to completely miss one of these two intervals. Okay? So now, although we are thinking about many intervals, we actually fix two concrete intervals, and at least one of them we have to miss completely. Okay, so the probability move from union bound on a lot to just, union bound on two events. Okay, and so now the probability that m sample miss, any of the two interval of epsilon over 2, you choose the right values, and okay. So what we got is we got that we had we get a case where we had infinite number of the concept class of size of infinite size, but we actually could learn it with very few samples. And in fact, the samples were only related to epsilon and delta, but nothing about the whole concept class. Okay, so the other question that we're going to study, or we're going to talk about, is this issue of frequent item set. I assume that being in KDB, you all know roughly what is frequent item set. So basically, think about a supermarket. Each row here is the set of is a purchase of a particular person, and you know the usual story. We want to verify that people who buy diapers also buy beers or whatever discretion. So we're looking for set of items that come together in a lot of transaction, and we so item set is a set of items inside the transaction. And we're looking at the frequency of item set, and we want the highest item set with a lot of high frequency. And the only thing I want to emphasize now, Matteo is going to talk about it later, is given a data set of transaction, I want to find the k most frequent item set. Doing it exactly is very expensive. Usually you can only do it for small item sets. Large item sets become exponential. And the question is, can we approximate it using a sample, approximate it good with a sample? And again, the problem, as I mentioned before, in order to have a rigorous answer to this question, we somehow directly or indirectly have to identify, in order to identify the top frequent item set, we in some way, we also have to somehow estimate the frequency of any item sets. Because if I say this one is the top, implicitly I say that the other one is not in the top. Okay, so somehow I have an estimate there. So I have to somehow have estimate of all of them. Okay. Okay, so we already said all this. So we need to estimate a lot of events simultaneously. Union bound is to lose. Sometimes we actually have to union bound on infinite number of concepts, so that's possible. So uniform convergence is a set of tools that allow us to, in a way, get a better union bound. Because in a way, what happened, union bound is wasteful because with some events that are not disjoint. And in a way, what VC dimension, you can actually see that it does it. It's a little bit harder to see it with the Rademacher average. It's just a smarter way to count. Okay, so there's no free lunch. If you're really something with all subsets of a large set, then you need a lot of samples. But when there is a structure among the events that you're studying, VC dimension and the Rademacher complexity capture that structure and allow you to cut on the union bound. Okay, so now a quick introduction to VC dimension. Okay, so I'll intentionally going to present it in the formal notation in which it appears in books and stuff, which is divorced from both learning and data mining, but it's important to see it in that way because it really generalizes the whole concept. So XR is a range set where X is basically a set of items, and it can be, well, that's important, it can be either finite or infinite. And R is a family of subsets. Okay, so that's kind of the most general thing you can have. You have a set of items, and on a set of items you have a family of subsets of that set. Okay? In the learning, X was R set of binary concepts, and okay, all this we saw before. Okay, so now comes the crucial thing. X could be infinite, but now let's take a finite subset of X, S, which has size little s. Okay, and now let's look at the projection of the range set, the projection of the sets on these subsets, on this subset S. Okay, so C is in the case of learning, or R in the general case. So basically what I'm saying now is I look at set S of elements, okay, and I now look at the set of concepts, or the family of sets, restricted to this finite set S, okay? And now I say, well, how many different sets are there? Okay, so at the beginning I might have infinite number of sets. But now I'm looking at a finite set of elements, and I look at the projection of these sets, the restriction of this set just to this small set of elements. And I ask, how many different sets are there? Okay, so this is the projection, okay, of our concept class S. Okay. Now, if this projection on S elements has 2 to the S sets, that means that our concept class can define any dichotomy, any any classification over the set S. So it's a very rich concept class. Okay? So in a VC dimension, I'm looking at the maximum S such that a concept class can define any partition, any dichotomy. Okay? So in the language of that area, if the projection on S has the full size, 2 to the S, we say that the concept class or the set R shatter the set S, okay? And the Vichy dimension of C is the maximum size S that is shattered, okay? Now, in some cases, it can be infinite. You can shatter anything. And in that case, the Vichy dimension is infinite. Okay, and just give you historic perspective, when Vapnik came with this idea, the idea was that if the Vichy dimension is infinite, you cannot sample it. And if it's finite, you can sample it. But he didn't ask, not being computer science, he didn't ask how many I have to sample. Just, oh, this can be sampled, this cannot be sampled. Okay, but we actually really want the values. This sounds very theoretical, so let's give you examples. Okay? So let's look at the example that we just did before, intervals on the line. Okay? So our concept class is the collection of intervals in AB, and how many points you can shatter? Okay? Well, so if I have 2 points, I can have interval that has both of them. I have an interval that take this one, I have interval that take this one, and I have interval that take nothing. I can shatter 2 points. I cannot shatter 3 points, because there's no interval that takes the 2 red and doesn't take the blue. Okay? So the VC dimension here is extremely small. It's 2, which we'll see in a second explain why we can learn it so fast. Okay? So the VC dimension of intervals on the line is 2. Just another example. So think about, this is the case of classification in machine learning. So you're looking at a partition of hyperplane to 2 by a line. Okay. So in 2 dimension, okay, how many points can I shatter? So I can definitely shatter 3 points. Okay, I can have a line that doesn't have that includes both of them on one side. I can have 2 of them in one. I can have these 2 in one. I can partition any 3. I cannot shatter 4 points. because there's no line that will put the two red in one side and the two blue in the other side. So on the 2 dimension, the VC dimension is 3. And it requires a little bit more work and a bit of geometry that in a D dimension, the VC dimension is D plus 1. Again, think about it, the number of concept, if you want, which is all the possible lines, is infinite. But actually the VC dimension is very small. Now we don't have time here to get to too much details, but I think intuitively you can see how this is related to overestimating in union bound. Okay, so if the shattering, if the VC dimension is small, that means that the event of this one, of this, and this one, and this one, and this one, they're all the same event. So there's no reason to sum over them. Okay, so the events here are included in one other. So they're actually, what the VC dimension basically says here is like, well, there are 2 or 3 real events. Everything else is just subsumed by these events. Okay, into the, okay. Okay. But now you've got the idea that everything has small VC dimension. No. So let's think about all the concept body, all the convex bodies on the plane. Okay, which is again something you really want to learn. Okay. Well, unfortunately, think about points in a circle. I know it doesn't look like a circle, but actually this is also quite a point. Okay. Well, I have a convex body that take any subset that you choose. Okay, any subset of point that you choose, I can put them inside a convex body and the rest outside the convex body. Okay, so the concept of all convex bodies in the plane has VC dimension infinite. Okay, we cannot learn that. Okay, so now you see, you know, there is a whole range. You can get very small VC dimension, you can get infinite VC dimension, you can get everything in between. You know, you don't have time for that. Okay. So now comes the crucial result, which historically, by the way, was known to the VC guys in the 70s, and then it took a good number of years to the Pak learner to discover it in the 80s. This is unbelievable. Okay, but if let's say be a concept class with VC dimension D, then it can be learned in a sample that is more or less linear in the VC dimension, and 1 over epsilon and ln of 1 of delta. Okay, by the way, this is not the tightest result. There's a slightly better result in space, but it doesn't matter. What's important is that the sample size is a function of epsilon, delta, and the VC dimension, nothing else. That's what I promised you at the beginning. I told you I'll develop a tool that would completely characterize the trade-off between the sample size, the accuracy of the estimate, and the complexity of the problem. So the complexity of the problem is the VC dimension, epsilon delta is the accuracy of the result, and M is the sample size. Okay? So here we get a result. Okay. Okay. I will not prove this, but it's built on what's called a Sartre lemma, and the only thing I want to show here is the following. So the Sartre lemma said the following. The Sauer lemma, it's actually a Schellach-Sauer lemma, show the following. If I have a range space with VC dimension D, okay, and now if I take a set S, okay, then the projection on the set S is bounded by n to the d. Now what's the meaning of all this? So remember, if it has VC dimension d, then up to d point, the projection is 2 to the d. Okay? But then once I go beyond the VC dimension, when my size, the size of the set is is above the VC dimension, now it goes polynomial in D. Okay? So it goes like n to the D. Okay? So at the beginning, up to D, it goes exponentially in the size of the set. And after that, it just goes polynomial in the size of the set. So remember, this is what I have to union bound on. This is the number of possible sets I have. Okay? And at the beginning, it grows exponentially, but with the VC dimension D, it grows polynomially. Okay? Good. That doesn't give you directly the results that I mentioned here. Okay? This requires some work. Okay? This we don't want. Okay, I have to switch file. I don't know why, but I have to switch file. Okay, so okay, so now we mentioned before this definition of epsilon net, so let me remind you again. And that's epsilon net for range space XR is a subset S, think about it as a sample, such that for every event that is not too small, our sample intersect with that event. Okay, that's the epsilon net. Okay, and the result that I showed before translate to the following. If I have a range space with VC dimension D, then a sample of that size, which is the same size we saw before for the learning, is an epsilon net. Okay? So again, the epsilon net, what is missing here? There's no mention here to how large is my universe. There's no mention here of the size of X or the size of R. The only thing that exists here is the VC dimension. Okay? Now the equivalent, which will be very important in the second part that Matteo is going to discuss, is that in data mining, in data analysis, we often want to actually estimate the size of subsets. How many of the population have this property, that property, and stuff. So the equivalent is something called the epsilon sample, okay? And an epsilon sample of a range space is again a set, which for us would be a sample, such that for any event, the probability of that event, or the size of that event, if it's uniform, minus the ratio of the intersection of our subset, of our sample, with that event divided by the whole thing. So the ratio that we get from our sample, the difference is bounded by epsilon. Okay, so if I sample these points and I normalize for the size, then I get a very good estimate of the size of the set, the probability of the set, or whatever. Okay. And the equivalent for the other theorem is this theorem. Again, this is not the best of the best. There are, people working on constant improving of this, but the bottom line is that, again, we can get an epsilon estimate with a number, with a sample size that is a function of epsilon and delta and the VC dimension, but nothing else. Okay, I put it slightly into proof, but I don't think I have time for this. So let me just tell you that the proof that the VC dimension is actually giving you, so I kind of made everything so simple. The VC dimension is related to how I cut on the union bound, and it all looks very simple, but actually it's not. And the real proof of this theorem, both theorems actually, is one of the most beautiful proof in probability theory. It has this double sampling technique. So okay, let me give you I give you 2 minutes idea. But this is just an advertisement to convince you at some point, when you really want to challenge yourself, to open a book and really look at this proof. Okay, because this is one of the most elegant proofs you ever saw. It's like at the scale of Cantor diagonalization. It's like amazing. Okay, so we have a range space XR. Okay, it has dimension D, and let M be a sample of M independent points in X. And sample is again either it's uniform or it's sample according to other-line distribution. That's the same. Okay. So E1 will be the event there exists a set in R. Probability of the set is not too small, it's at least epsilon, and our sample didn't hit it. Okay, the intersection of our sample and that set is 0. Okay, so the only thing we have to show is we have to show that this probability is bounded by epsilon. Okay, but of course the problem here is that there is a quantifier here, is there exists an R, so we have to show it on all possible R's. And a priori, R can be infinite, and also X can be infinite. So the only trick is, how do we replace this by a finite thing, a small one? Okay. So now we choose a second sample of the same size. Okay, for the other proof, we actually need the larger size. But for this one, we choose another set of the same size, and we call it T. So now we have 2 samples. Okay? And now we define another event, E2. And E2 is the probability that there exists R. Again, R has probability at least epsilon. Again, intersection of R with M was empty. But the intersection of R with T was reasonable. Now what's reasonable? So think about it. The probability of R is at least epsilon, and the sample is size M. So the expectation, you expect the intersection to be epsilon M. So I just want it to be half, at least half the expectation. Okay? So now what we're going to show is we're going to show that the probability of E2 is a good proxy for the probability of E1. Okay, so why this is true? Okay, so definitely E2 has another condition compared to E1, so the probability of E2 is smaller than the probability of E1. But the condition that we added has, very high probability. So it cannot restrict the probability by too much. Okay? So the probability that T time R is smaller than epsilon M over 2 is smaller than half. You can use Chebyshev, Chernoff, whatever you want to show that. Okay? So let's keep this. This is just technicality, but the probability of E2 divided probability of E1 is the conditional probability of E2 conditional E1, which is exactly the probability that we get at least this number of samples, so the probability is at least half. And therefore, basically the high-level thing is the condition is so large, its probability is so large, that the probability of E2 is at least half the probability of E1. Okay? So now, remember, E1 is the one I want to bound. Okay? So instead, I'm going to bound the probability of E2. Okay? That's going to be good enough. Okay. So far, nothing smart. Okay. Now comes the punchline. Okay. So just up here is the event that we want to bound, E2. Now let's make E2 simpler. Make it simple, forget about the requirement that R is greater or equal to epsilon. Okay? So definitely E2 prime has probability larger than the probability of E2 because we just throw away a condition. Okay. Now comes the punchline. So now focus. So now we look at E2 prime and we say what it says. It says there is sample M that has intersection 0 with R, and there is another sample T that actually has a very good intersection with R. Okay? Well, so let's restate it. Let's assume that I take a sample, which we call here Z, of T of 2M elements. Okay, so I take a sample of 2M elements, and only after I take the 2M elements, I partition them randomly to two samples, T and M. Okay? Well, that's the same thing. I mean, these are two random samples, so I could well take 2M elements and partition them to two sets of M. Okay? So now comes the question, so now the event E2 prime is bounded by the following question. Taking 2M elements that have together at least K intersection with R, what's the probability that when I split them, one half has no intersection at all with R, and the other one has all the intersection with R? Okay? You believe me that this has very small probability. Okay? Okay? So the probability E2 is now reduced to the following question. Take 2M elements. They don't even have to be sampled. They don't have to be random. Take 2M elements such that they have intersection at least K with R. What's the probability when I split them to two? One of them has no intersection with R and the other one has K intersection with R. There's still a problem that I have to argue about all possible R. Okay, so now comes the technique. Okay, so for a particular R, let's ask, what's the question? Now the set Z, which is this 2M element, is an arbitrary set. For a particular set R, we ask what's the probability that the intersection with M is 0. When I partition it randomly, the intersection with M is 0, and the intersection with T is greater than K. Well, obviously that has a very small probability, and we compute it there, and it's bounded by exponential in M and epsilon. Okay? That's for a particular R. Okay? But now comes the question, how many R's do I need? How many different sets I have to union bound on? Okay, so that's the probability that it won't happen for one particular R. Now comes the real punchline. How many R's do I need? Okay? Well, remember that I'm only talking about the set Z. Okay? How many R's are, how many different R's exist in the restriction to Z? That's the VC dimension. Okay? So for an arbitrary Z, the projection of R on Z, well, has no more than this number of different sets. So now the possibly infinite became just a polynomial in D. Okay? Now this is where we use the VC dimension. Okay? So now the probability is bounded by the union bound on this number of sets, by the probability for a particular R. And now you do some really unpleasant calculation and you get the end. Okay? If you see it the first time, believe me, you didn't see how deep this argument is. It's, you know, it's very deep and it's beautiful. Okay. This goes to Vapnik. long before there was machine learning and long before there was theoretical computer science. Okay. It's almost bound. It's almost tight. I wouldn't discuss it. You can show that with VC dimension D, you need at least D over epsilon samples in order to detect. So that's that. Okay. Okay.
I think you skipped the Rademacher slide. No?
No. What I skipped here is there's a minor technicality that when you do learning, then you think about the VC dimension of the concept, but actually you need the VC dimension of the difference between the concept and the correct one. There is some technicality here. It's important in machine learning. Let's skip it. I just tell you that I cheated you a little bit, but it's okay. Okay, so now okay, so that's VC dimension, and maybe solve all our problem. Well, no. So there are two problems with VC dimension. Okay, the first one is it's very hard to compute. Okay, I'll show you some simple examples, but Matteo will show you later when you actually compute VC dimension to practical problem in data mining. It requires hardware and actually very genius ideas. Okay. There is another problem, which is that embedded in the idea of VC dimension is that this is just a combinatorial concept. We didn't talk about the VC dimension, how it's related to the distribution about the elements. Maybe all the concept, all the complexity of the complex, of the complexity of the problem is hidden in an area that has relatively small probability. Okay, we look at it as a combinatorial concept. So we might actually overestimate the complexity of the problem because we ignore the probabilities. Okay. So Rademacher average is a more modern concept that gets, to some extent, well, definitely get around the second problem, maybe get around the fourth problem. So first of all, embedded into it is the input distribution. Okay, so we're actually going to estimate complexity as a function of the input distribution. It's very important for data mining. It's not only for classification for 0-1 function, but it applies to any functions. Okay, any possible function. You can show that the result you get for classification using Rademacher complexity are at least as good and sometimes better than what you get from the VC dimension. It can be computed from a sample. To some extent, also VC dimension, in some cases, can be computed from the sample, but in Rademacher complexity is well defined that you can actually compute it from the sample, but it still can be hard. Okay, so not free lunch. It still can be hard, but can be done. And Matteo will show you in the second part. He can do it for a very good, important problem. So here's the intuition of Rademacher complexity. Okay. So assume that S1 and S2 are two samples, and good enough samples. Okay, uniform convergence is just good enough samples. Okay. And they're good enough samples for estimating the expectation of any function in a family of function f. Okay? So that means that uniformly over all function f, if I take a sample S1 or S2, it gives me a good estimate. Okay. What does mean a good estimate? It means that if I average over the values that I get of fx over the sample S1, well, if it's a good estimate of a fixed value, then it should be very close to the same estimate using the second sample. And both of them have to be very close to the real expectation of f. Okay? Well, another way to write it is that the soup over all the function in f, okay, the estimate of the expectation you get from S1 and the estimate of the expectation you get from S2, okay, the expectation of the difference is bounded by epsilon. Now, in case there's someone here from mathematics, I say right away that I ignore all issues of measures and whatever. Everything has to be phrased with measurable, We'll forget about it. Here, we are in computer science. Okay. So, another way to say that S1 and S2 are sufficiently good uniform convergence samples for the expectation of any function in f is that the soup over f of the difference between one sample, what you get with one sample, the difference we get, what you get in another sample, expectation of this is, expectation of the S1 and S2 is bounded by epsilon. Okay? What Rademacher says is, instead of taking two samples, S1 and S2, let's take one sample and split it randomly in many ways. Okay? So the Rademacher variables that, by the way, come up in other places in mathematics are sigma 1 to sigma m, which are IID, random variables, probability, they are either -1 or 1, with probability half. Okay? And the empirical Rademacher average of the set of functions f, okay, is the expectation over the sigma, over all possible partitions, okay, of the soup over all functions. Now, this is a short way of writing this, okay? Take the plus ones minus the minus ones, okay? Take the estimate from the plus one minus the estimate of the minus one. These are estimate of the expectations. And take the soup over all f, okay? So that's how you'll see it again, don't worry. Okay, so that's one way to look at this, okay? Here's another motivation for the same. You know, a good thing, a good concept has a lot of motivation. Okay, so here's a different motivation. Assume, let's go back to classification. Assume f are a collection of 0, 1 functions. Okay? A rich concept can approximate any possible dichotomy. Okay? So remember, if something is very rich, any possible characterization can be formulated with one of the functions in f. Okay? Well, in particular, it should be able to well approximate a random dichotomy, the sigmas. Okay? So the Rademacher average, okay, is basically the expectation of how good you're estimating. Is there a function that estimates correctly the sigma i's? Okay? Okay. So, in other words, the Rademacher complexity, this is an example on classification, but also in general, is a measure of how rich, how expressive is the set capital F of function. Of course, the richer it is, you'll need more samples in order to estimate. Okay, so now we have to go a little bit more formal. The way we define it with respect to a particular sample. Okay, so that's a very practical way. You sample and compute this. That's the empirical Rademacher average. And now you can come with the Rademacher average, which is the expectation over the empirical expectation over all the samples of the sample, all the distribution of the sample. Okay, so you estimate, you take expectation over all possible samples, and you get the Rademacher complexity. So this, in a way, is a random variable of the sample, and this is now a fixed value. Okay, so these are the Rademacher complexity. Okay. Question? Okay. So the major result, and I will go through the proof here, is the following. Let expectation of fz, this is the one we want to estimate, okay? And we estimate it by just taking the average over the sample, okay? So this is the error in estimating a particular function f. But we want our sample to estimate all the functions simultaneously in capital F. So we take the soup of the arrow over all the functions, okay? And the major result is that the expectation of this, or the expectation over what? The the expectation over the sample S. Okay, so if I sample, so now think about, there's like too many notations here. So think about the following experiment. I sample S, sample of F, M elements, okay? And I choose some function of F to estimate it using the sample. How bad can it be? What's the worst error can be over all the function if on F? Okay? So the expectation of the worst error, or the soup of the error, is twice the Rademacher complexity. Okay, so the Rademacher complexity gives us a bound on the maximum error, the expected on the sample of the maximum error over all functions in my class. Okay? And so this is actually the basic result. You hardly see it in computer science because they always jump, this is the proof, I will do it, they jump to a bound. Okay, so basically it says that for a sample S of M, there should be M elements, and from some distribution D, lambda, delta ends of 0, 1. For all F simultaneously, the error in estimating F, the error between the real expectation minus what you get from the sample, okay? The probability that it's greater than twice the Rademacher complexity plus epsilon is exponentially small in M and epsilon square. And CC is the variation of the function, just ignore that. And what I really want to show you is that we can write this, and that's the important thing here. You can write it in two ways. This is the absolute Rademacher complexity. This is the empirical Rademacher complexity. Okay? And you just add another epsilon to the error. Okay? Okay? And I have 2 minutes, so let me just tell you, just give you the phrase, how do you prove it? It actually, if you look at, there is a machine learning book, they made the big fuss out of the way it's proven. But actually, if you count from probability, what happened here is basically you do something called, so you look at it as a martingale, and you do a Zuma inequality on so they call dog martingale, so the whole thing is actually a standard probability. But in machine learning, they like to call it McDermott inequality. I know McDermott, who's a great probabilistic, and I assume that he also looked at it kind of strange that that's why he's so famous for. Basically, it says that if I have a function on n variables, and our function now is going to be the expectation over n samples, and if a change in one variable can change the function by no more than a constant, then the probability that the value that I get from the sample of n elements minus the expectation of the variable, the probability is greater than epsilon is bounded by what's written there, and it looks somewhat familiar to Chernoff bound, and Azuma is Hofding bound, which Chernoff bound is a Hofding bound, and Hofding bound on martingale is the Azuma, sometimes also called Azuma Hofding. So it's all related with a large deviation bound. It's kind of standard. Okay, and the result that Matteo, and I'm finishing here, the result that Matteo will show later is that you can actually compute. So far, let me just say. So far, it looks very hard because this Rademacher complexity, well, this is easy, but I have to take soup over all functions. I might have infinite number of functions. How do I do this? Okay, so that's the problem. And like VC dimension, you need some, creative idea to compute it. It's also you need some creative idea how to compute it. It's not a straightforward thing that you do. And there are several ways to do it. This is now very, very recent, development in this research. There are various ways to estimate Rademacher complexity. One way to look at it, one way to do it, not necessarily the best one, is the following. Given a sample, look at fz1 to fzm as a vector. Okay. Now this is the L2 norm of the vector. Okay. Now this is for one particular f. We want it sup over all f. So if the maximum L2 norm of the application of the vector on of the function on the sample is bounded by some constant c, then surprise, surprise, the Rademacher complexity can be bounded by some very, well, at least when f is bounded, can be bounded by relatively easy thing to compute. Okay, so this was just to show one slide example that what looks like very complex, it is very complex in general, but in many ways there are concrete ways to compute the Rademacher complexity. We'll stop here for a break, and then Matteo, when do you want to start?
No, I think there is a break until 11. Maybe wrong.
Okay, so let's start 5 to 11 here.